Yeah, my aunt's still got
So I'd like to do a little bit of an intro into the next unit, 10.1. But this won't take very long, and then we can use the second half of class to continue practicing for Tuesday's tests. I think potentially what we need most practice with is area, especially finding polar area between curves. So yeah, but there's another worksheet that you guys picked up, and we can practice problems off of that worksheet. So sequence is just a collection of numbers that follows a rule. So if we want to write terms of a sequence, we can plug 1 in to find the first term, plug 2 in to get the second term. So for instance, the terms, the first 5 terms of this sequence is -1, 5, -7, 17, -31, just using basically like a function, right? We're just plugging in and finding certain values. So for instance, just to show you, a sub 1 would be equal to 1 plus -2 to the first power. So 1 minus 2 is -1. So a sub 1 is -1. A sub 2, plug 2 in for n. 4 plus 1 is 5. So a sub 2 is 5. A sub 3 is -7. A sub 4, plug 4 in, we get 16 plus 1 is 17. And a sub 5 is -31. Okay. So sequence is a collection of numbers that are in a 1-to-1 correspondence with a positive integer. So that means if I plug in a specific number, I'm only going to get one number in return. I'm not going to get 2 numbers in return. So we're not adding these terms together. For sequence, it's just a collection of numbers, usually separated by commas. So, but these are the sequences that we're more interested in. So let's say we have a monotonic sequence. That just means that your sequence, your number values are always going to keep increasing or always going to continue to decrease. So sometimes a sequence of numbers can do this, where let's say if you were to graph all these numbers, they end up looking like this, where they're always increasing, but you can tell that it's heading towards some upper bound. Kind of think of it as maybe like an asymptote, right? So when we have a bounded sequence, that's when you can kind of tell it's yes, it is always increasing, but it's like 7.9, then 7.99, then 7.999. So it's obvious that it's headed towards some bound. So sometimes you have a sequence where there's a clear upper bound. Sometimes you have a sequence where there's a clear lower bound, because the number will keep decreasing, but it's predictably decreasing headed towards a certain number. If I have an infinite series, that is when we're adding, we're basically taking a sequence or rule of sequence, and we're adding all those terms together. So infinite series is when you take a sequence of numbers and you add up those infinite number of terms. The sum may add up to be infinity, but not always. So sometimes the infinite series can be converging, which means that if I keep adding the sum of terms, the terms before, if I keep adding terms to it, it's still headed towards a predictable numeric value. But sometimes an infinite series, depending on how large the next value is, may sum to be infinite. So if a series sums to be infinity, we call that a diverging series. But if it sums to be a real number, we call that a converging series. A partial sum is the sum of the first n terms. So if I want to find a partial sum of a series, maybe it's the sum of the first 10 terms or the sum of the first 20 terms. But it's only a partial sum. It's not adding up all the terms, just adding up the first n terms. So a sub n would give you it's an expression that gives you the nth term in the sequence. But S sub n is an expression that gives you the sum of the first n terms of the sequence. So a S sub 5 is different than S sub 10, different from S sub 20, just in the sense that it's either the sum of the first 5 terms, the sum of the first 10 terms, and sum of the first 20 terms. So number one here, use the following sequence to find a sub 4 and s sub 4. Well, a sub 4 is just the fourth term in the sequence, but s sub 4 would be adding the first 4 terms of the sequence together. So this rule just says that if I were to add up all the individual sequence terms, it's the same thing as looking at the sequence of my partial sum. For the infinite series, the nth partial sum, S sub n, is equal to a sub 1 plus a sub 2 plus a sub 3 dot 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 a sub n. If the sequence of the partial sum converges to some known number or some real number, then the series adding up the individual terms is going to converge. The limit S is called the sum of the series. Likewise, if my partial sum diverges, then my series will also diverge. So number two, does the series converge or diverge? So meaning if I were to add up all these terms like 1/2 plus 1/4 plus 1/8 plus 1/16 plus dot dot dot, is the sum going to eventually head towards a predictable number, or is it going to jump up to infinity? If we're continuing to add these numbers up, is it going to converge to a number or diverge? So a way to test this is looking at the partial sum, looking at the pattern of the partial sums and seeing, does the partial sum look to head towards a specific number? So here's an example here. So the partial sum S sub 1 is just my first term, which is 1/2. So I'll just right. So a partial sum allows us to kind of break this down and look at it in individual parts. So partial sum S of 1 is just 1/2. Partial sum S of 2 is just 1/2 plus 1/4. Partial sum S of 3 is just the first 3 terms added together. And partial sum S of 4 is just adding the first 4 terms together. And if we look at these numbers can kind of give us a clue as to, is the sum of all these numbers going to be potentially headed towards a real number? And because the 1/2, 3, 4, 7, 8, 6, 15, 16 kind of feels like it's headed towards a certain number, we can predict that potentially that this sum will head towards a predictable number, because these numbers are all increasing, but it looks like it's headed towards 1, right? So an easy guess is that the partial sums are getting closer to 1, which means that if I were to add up all these infinite number of terms, that it should approach 1. So this is just a strategy for us to use partial sums to give us insight as to what's happening to the series. So here the sum converges to 1 since the sequence of the partial sums approaches 1. Number 3, use a calculator to find the partial sum of the series. If we were to plug 1 in, then 2, and then 3, and then we're adding up all the, let's say we want to add the first 200 terms, or let's say we want to add the first 1,000 terms. Let's see if we can find some pattern. We can make the calculator do this work for us. So in your calculator, you're going to do math 0. Sorry. Follow along this. You can do that. Do it during advice. Okay, go to math 0. Math 0 will give you that summation notation. And we're just going to type in what we see there, but you're going to use x as your variable. So you're going to say the sum x equals 1 to 200. Then type in that rule of sequence, which is 10 over x times x plus 2. It may take a moment for it to give you that sum, but here the sum ends up giving us 7.45. And do the same thing for adding up the first 1,000 terms. So change the upper bound to 1,000 and see if the number changes much, right? If it changes by a ton, then you know it's probably not going to be a converging series. But if it's just incrementing slightly, then looks like there could be a ceiling that the sum of terms is headed towards. $7.45 is the sum of the first 200 terms. 7.49 is sum of the first 1,000 terms. So what's a prediction that you can make? That the sum is going to be what? 7.5, probably, right? I mean, we could test, right? 2,000 terms, 3,000 terms. It's probably going to be like 7.49999. So this just to kind of demonstrates what we're eventually going to do, because we're going to basically learn a bunch of rules that will allow us to look at the pattern of, or the way that the rule of sequences is formed, and look and determine, is it a converging series? Is it a diverging series? A lot of times, most of these rules are not going to be able to tell us what the sum will actually be. Some of them will, but some of them we won't. But the most important thing, at least the first half of this unit, will just be, can we determine whether the series, based off the rule that we see, is it going to be a converging series or a diverging series? And here, in this case, we can tell by just doing a couple of checks that it's probably going to be a converging series. But we're going to talk about certain rules in place that will eventually allow us to look at that and tell, okay, this is definitely a converging series because of these properties. Next up, number 4. Does the series converge or diverge? Summation of n. So you have 1 plus 2 plus 3 plus 4 plus 5 plus 6. Our guess is probably not, right? All those numbers, they keep increasing. And if I keep adding larger and larger numbers, that sum is going to continue to increase without bound. A way for us to see it played out from a partial sum's perspective is looking at the partial sum, or looking at the sequence of numbers within the partial sum. So here, partial sum of the first term is just 1. Partial sum of the first 2 terms is 1 plus 2, which is 3. Partial sum of the last next 3 terms is 6. And a way to look at that partial sum and be able to tell that this is not going to be a converging series is look at the sequence of numbers there. 1, 3, 6, 10. Those partial sum sequence of terms is also not headed towards a specific number. So because the partial sum, the sequence of partial sums is not headed towards the ceiling, we can also conclude that this series is not going to converge, but it will diverge. Okay, we can pick some of this up again tomorrow, but I would like for us to look at that worksheet that I gave you with polar area. So polar area here for number 23, this one says we want the region that is inside r equals 2 sine theta which is inside this top circle, but then outside the r equals 1. So ultimately, we are targeting this region here. That's our ultimate goal here. But polar area doesn't work in the sense that we would expect with rectangular area. We can't just say, oh, this curve minus this curve, and then that's the region here. Sometimes it is, but also we want to kind of understand how polar area is formed. So the first thing is understanding that the bounds will play a role, right? So a lot of times, if you're looking at intersections between two graphs, you're looking at the bounds between the two curves. So let's just set these equal to each other to find the intersection between the two curves. So sine is equal to 1/2 pi over 6 and 5 pi over 6, first and second quadrant. So the strategy is, what if we can find the area of this entire region? Because anytime we're wanting to do anything with area, we have to involve the polar zero. So the strategy is, what if we found the area of this entire region first? And that entire region is not the answer, but it is going to be something that we can eventually subtract from. And we know that that is referring to that r equals 2 sine theta. So that will give me the area that I want to subtract from. So integral, 1/2 integral from pi over 6 to 5 pi over 6 of that 2 sine theta squared d theta. So that will give me sector area accumulated from one bound to the other. But that's not what we want, right? We want to subtract out the portion that is part of this lower circle. So let me indicate in red what I want to remove. I want to remove all that area. So I want to subtract this region. So minus 1/2 depth integral from pi over 6 to 5 pi over 6 inside this r equals 1 equation. So 1 squared d theta. Any questions? Practice plugging that in the calculator. Okay. Try 24. Start off with your intersection. I like to use symmetry. I like to just find a portion of the region that I need, and then sometimes I can just double it, especially if I see a nice symmetry. So try that. Let me come around and just see if you need any help with these area problems. The 2 sine theta is this node. That's already good. Yeah. So this first integral will be this entire region. And then we want to subtract out this portion in red that we don't want. see if we'll apply that for 24 as well. So I would do the larger region first. So why don't we find the area of this entire region? And we can subtract that one. Find the intersection first. So remember the reason that I drew all these out is because all the area is formed not with rectangles, but with these sector regions. So they're going to start off here because this is theta 0. It's going to put theta 0 to that point here. So it's going to accumulate all these values. And find where that intersection is. That will give you the area that's more than you need, and then you can subtract out this region involved in this. Well, we only care about the region inside this circle, but outside this circle too. So ultimately, we just care about this region. But I'm just going to focus on this part because I know if I get that, I can double it. You may want to put that square outside because it looks if you want to put additional parentheses around the 2 sine theta, and then the square outside. Or what I do is I like to have this stored under y1, and then just do y1 squared. That way you can do a thing from this. R equals 2 is a circle that represents that. It's a circle of that center that's 0. So
That's Mark. That's okay.
just something that data. So all the different.
No, there's no good.
Everybody okay with 24? I just want to focus on that top region, but you may have a different strategy. You may want to go from -5/3 to 5/3 if you want to include this entire region. But I like to just focus on the smaller region and so that way, to me, it's just less to think about in terms of my bounds. Any questions with this? All right, let's see if we can try 24. Next page. Sorry, 25, next page, 25. Right, see if you can identify the region that the problem is referring to, and then you're going to strategically try to get that region, but you're going to have to involve areas of both, either you're adding or subtracting potentially to get to that region that you care about. Now I want to subtract out this region back. This is the region that is. That's a formula. The area formula is 1/2. Or polar is 1/2 integral of A to B r squared b. Because the area of a sector is 1/2 r squared beta, so that's just adaptive. Now we're adding infinitely thin sectors from one end to the other end. So sometimes it may be helpful for you to create a table of values so that you can kind of have an idea where both of your graphs are starting and kind of have an idea, okay, this graph is starting here and it's moving in this direction. So this 25 here, I'm looking for the intersection where sine of theta equals 1 minus cosine theta. It's kind of hard to solve, but if we rearrange it, maybe it's a little bit easier to think about, okay, what theta will allow sine and cosine to add up to be 1? Well, pi over 2 can work because sine of pi over 2 is 1. Cosine of pi over 2 is 0. So 1 plus 0 is 1. So the intersection is at 0 and pi over 2. So if I want to find this outer region, I first have to figure out this entirety. Remember, anytime you want to do area, you have to stem from polar 0. And then I can subtract out the region in red, and that will give me that outer region that I want to leave in my answer. So if you guys see that, where if I can find the area of this entire region, that's more than I need, but I can start off with that, and then I can subtract out everything that is hitting this 1 minus cosine theta. And if I can take this large region, subtract out that region in red, what's left over is this region that I want. I'll give you the slope, but it's not going to give you the area. Not by graphing, no. But I mean, but you're not doing any calculus. You're just making the calculus do all the work for you, right? You don't do any, yeah. So we're skipping all that process. It's really just setting up, right? If you can set up the problem, then you pretty much have your answer.
Outside, the sine is that.
Yeah, so that's something that we need to know. Your sine theta will be a circle. Your 1 minus cosine theta will be like a Lima sign. And if you want to build it, you can build it from scratch. Right? At 0 is 0. At pi over 2 is 1. So this one here, starting at 0. At pi over 2, it's 1. And then at pi, it's back to 0. So it's got to be this one, right? This is kind of building. All the graphs will kind of go in this direction. And this one, r equals 1 minus cosine theta. Here, this one, if I plug 0 in, I get 1 minus 1, which is 0. So this one also starts at 0. At pi over 2, it's also at 1. But then at pi, it's over 1 minus cosine of pi. Cosine of pi is -1. 1 minus -1 is 2. So pi is all the way over at 2. So that must be referring to this graph. Oh, here are a couple of reminders for that will be helpful. Your limacons, your even petals, your circles are all going to have an interval from 0 to 2 pi. It'll take that long for it to complete a cycle. But your r equals cosine theta, your r equals sine theta, any odd number petals, the interval is just from 0 to pi. And your homework off of 10.1 is just pages 3 and 4, just to kind of practice finding sequence of terms, finding partial sums. So I'll send out a reminder this afternoon. So page 3 and 4 off of your 10.1 is your homework. Tomorrow we'll continue with our notes, but then we can always come back to this and do more polar area of practice. All right, can I get your phones?
It's all like part of it. You know, 3 people.